give you an idea where we're headed, this is 2-6, so we're looking at functions today, and if you looked at the way I spelled that, we're going to take a look at functions. I know, very creative. And then 2.7 we will cover when I see your bright shining faces again on Wednesday, and 2.7 is going to be our last section in Unit 2. So that means on Wednesday we will review for your test. We will also have a quiz. Actually, no. Wednesday we will cover 2.7. We have a quiz over 2.5 and 2.6 on Friday. And we will review for the test on Friday, and then you will take your test next week. Okay? So in 2.6, we're going to look at functions. In other words, how do I determine if something is a function or not a function? So we're going to talk about 2 ways to do that. We're going to look at taking whether it's a relation or a function and writing it different ways, whether it's as a table, as a set of points, on a graph, or in a mapping. And then we're going to look at the domain and range of functions, and we're going to review all of your vocabulary, input, output, domain, range, independent, dependent, so that you understand how to do all that. All right, so a relation is simply a set of ordered pairs or a set of points. So anytime I have a set of points, I have a relation. I don't know whether my relation is a function without verifying a few things. But every function is first a relation. A relation is just some ordered pairs. It could be a multiple, 3 or 4 ordered pairs. It could be 2 ordered pairs. All I know is I have a set of ordered pairs. So I've given you that here. I've given you 3 ordered pairs, the point 2, 3, 4, negative 2, and 6, 1. What do we list first in an ordered pair? X or Y? X. So these are always X, comma, Y. And if I have a set of ordered pairs, I can write them as a table. So I can always take any of my points and rewrite them as a table. So the points just simply go together. So 2, 3 would be 2 in the X column, 3 in the Y column, side by side. If I had the table from there, I could read that that was the point 2, 3. So then I have the point 4, negative 2, and the point 6, 1. So I can start with points and write them in a table. I can start with the table and identify the points out of the table. Occasionally, our tables will be flipped on their side. So instead of giving you a vertical table, you might see a horizontal table. And I show you this because it kind of stunned a bunch of calculus teachers a couple of years back when they had horizontal tables on the calculus exam. And the kids didn't miss the calculus. They had no idea how to read the table. They read the table wrong. So if I have a horizontal table, my X and Y still go together. So if my X is 2, the corresponding Y is 3. They still have to be listed next to one another. So that's 2, 3. Then I'd have the point 4, negative 2, and I'd have the point 6, 1. And horizontal tables are becoming more and more common in textbooks and on exams because they take up a lot less space. And when somebody's typesetting an exam or a textbook, this is a lot cheaper and quicker for them to typeset a horizontal table than it is to typeset a vertical table. And if you've ever tried to type one of those in like a Word document, move it around, you can probably know what I'm talking about. All right, so I can have a set of ordered pairs. I can have a table. From the table, I can get the ordered pairs. I can also have a graph or a mapping. So a graph, you guys have been graphing since what, 6th grade? 7th grade? When did y'all first start graphing? Not last year. All right, so the point is 2, 3. That means I start at the origin. I go 2 to the right for X and up 3 for Y. So there's my point. 4, negative 2 would be 4 in the X direction, 2 down in the Y direction, and 6, 1 would be a point. Each of these representations, the multiple representations of a relation, just gives me different information, okay? The really nice thing about the graph is I can very quickly determine whether or not this is a function by doing the good old-fashioned vertical line test. So the vertical line test is where I take a vertical line and I drop it somewhere along my function. And as long as it touches only one point at a time, that's 1 point, that would be 1 point, that would be 1 point, then this passes the vertical line test. So I know that it's not just a relation, it's a special type of relation called a function. Kind of like all squares are rectangles first, but not all rectangles are squares. All functions are relations, but not all relations are functions. So you should be able to take points and graph them. And then there's the good old-fashioned mapping. A mapping is just where I take all of my x's and all of my y's and I show how they're related to one another. So on a mapping, I list each x once and only once, and each y once and only once. And order does not matter, but a lot of times on a test you'll see them in numerical order. So if I list all my x's in numerical order, I have 2, 4, 6. If I list my y's in numerical order, I'd have -2, 1, and 3. And then a mapping just shows the relationship. 2 goes with 3, 4 goes with -2, and 6 goes with 1. And so on a mapping, I can tell if something is or isn't a function because each x should be paired with only one y value for a function. So 2 should be paired with one y value, 4 should be paired with one y value, and 6 should be paired with one y value. All coming back now. It's like dusting out the cobwebs. Okay, so the question was, isn't there a situation on a mapping where somebody can have two? Okay, we're just going to do this. Watch this. There. We're going to go here. So I could have a mapping that looks like this. So my first mapping here is a function. Each x has one y value. 1 has only one y value. 3 has only one y value. 5 has only one y value. But the second mapping here is not a function because 1 cannot go to both 2 and 3. Each x can only have one y value. So this would be a function. This would be not a function. So he would simply be a relation. If I graphed these in a table form, this would be 1, 2, 3, 2, 5, 2. And if I graphed those, they would pass the vertical line test. If I took the math and made it a table, I'd have 1, 2, and 1, 3 as separate points, and that would fail the vertical line test. Domain and range again. If we go back to domain and range, domain are my what values? X values. So domain are my x values, range are my y values. So in this, if this is discrete data, I have just individual points. I don't know how they're related to one another. For domain, I'm just listing all the x values, 2, 4, 6. And for range, I'm listing the y values, 3, -2, 1. If I have a y value or an x value that repeats, I don't have to list it more than once. We're keeping it simple, right? All right, so some terms that we might want to become familiar with. We have discrete data, or discrete variables, and continuous variables. If I think about these on a number line, like 1, 2, 3, 4, 5, 6, if I have discrete variables on a number line, they will be graphed independent of one another. I won't connect them. If I graph them in an xy coordinate plane, discrete variables will just be listed. They won't be connected. I don't know the relationship between them. I can't connect them with a line. We typically see discrete variables, things that we count. So numbers that we count. Like this could be the number of AP, pre-AP classes that you're taking. Well, you don't take 1.5 pre-AP classes. You either take one or you don't take one. So 1, 2, 3, 4, 5, 6. Ooh, or 0. Well, no, not y'all. You're in pre-AP class here, right? So discrete things are things that I might count, that I can't have fractions of. Now, one that I could probably give you an example of that's a little bit weird would be shoe size. You can wear a 6 or a 6.5 or a 7 or a 7.5. You can't wear a 7.3829. It doesn't exist. That shoe size does not exist. So these are individual discrete variables. You either wear a 6 or you wear a 6.5. There's nothing in between the two. Continuous variables are connected. So if I graph continuous variables on a number line, I would be talking about everything between 2 points. So I'd have the line connecting. How many points are there between 4 and 9? An infinite number, right? There's an infinite number of points between any two numbers. So I could think of this as maybe the mile time for cross-country runners. So maybe you run a mile in 4 minutes, or 4 minutes 1 second, or 4 minutes 2 seconds, or 4 minutes 3 seconds, or 4 minutes 4 seconds, and so on, all the way to 9. You could even run it in 4 minutes and then fractions of seconds, right? You don't have to have just 1 second. You could have 1.5 seconds, or 1.28346925994 seconds. I mean, it depends on how precise your measuring device is. That's the only restriction for things that I measure. So if I was going to go to the pool with you and we were, timing to see how fast you swim and I'm timing you on my old watch, I could get it down to maybe the second. If you have a stopwatch, maybe fractions. If you watch the Olympics, a few years back, 2 Summer Olympics ago, it was literally the difference between first and second place, they were saying, was how long a fingernail was when it hit the wall. So like somebody with longer fingernails and shorter fingernails, that was how close first and second place came. So it was one of these pictures too, where you kept looking at the picture. Do y'all remember this? You might have been too young. They kept zooming in on the picture because the guy that hit first really did have a longer fingernail, so it looked like he was not even touching the wall. And the other guy's hand was like right on it, but he came in second place because the first guy literally hit that wall. I mean, we're talking fractions of a second. So continuous variables are things we measure. So these are measurements. So this is maybe height, weight, speed, things that we measure are continuous. And then we have independent variables and dependent variables. And so independent variables are those x or y, typically in algebra. X and dependent variables are usually y's. So we can have blah, blah, blah depends on blah, blah, blah. Whatever we put in this first place is our dependent variable. Dependent. Whatever goes here is our independent variable. A dependent variable will depend on something else. So if you are ever out and about eating dinner around prom time, you can see a beautiful example of dependent variables at work. If you go to a nice restaurant and there's all the kids there for prom all dressed up, you ever been out to dinner and seen this anomaly? There's like a table of like 12 kids, 6 girls, 6 boys, all on a date, all up for prom, right? The girls are wearing the big shiny dresses, the boys all have their little tuxedos on. A perfect example of a dependent variable, if you just watch the table for a minute, somebody will start it, somebody will get up and go to the bathroom. If a girl gets up to go to the bathroom, what happens to the other 5 girls sitting at the table? They all go to the bathroom, right? And suddenly you looked, it was the 12 beautiful high school people all dressed up, and the next time you look, there were 6 dudes sitting by themselves wondering what happened. It's because girls are a perfect example of dependent variables. One goes, I'm going to go to the restroom, and 5 others go. It's like a herd of girls. Guys, you know what I'm talking about. And girls, you scare them. You freak them out when you do this. Because they're left staring at each other wondering what you're talking about, okay? It's really not nice. But it is a good example of dependent variables. That or your friend that calls you and says, like, what are you doing tonight? Because I was thinking about doing something, but if you're doing something else, I'll do what you're doing. That is your dependent friend, okay? Dependent variables depend on somebody else. Now, in an effort over the years to teach this more effectively, I have come up with the function machine. For any function that exists in the world, we have an input to that function and an output. And for the first 11 years of my teaching career, the best example I could give of an input-output was the M&M's chocolate covering machine. Whatever you put in comes out covered in chocolate, right? So if I put a peanut in, I get a chocolate-covered peanut out. If I put a raisin in, I get a chocolate-covered raisin back out. If I put a pretzel in, I get a chocolate-covered pretzel back out. That is the goal of the function machine. If I put a dirty old sock in, I get a chocolate-covered dirty old sock back out. This function always covers everything in chocolate. Okay? So for every input, there is only one output. If I put a peanut in there, I cannot get a yogurt-covered peanut back out. It's a function. For each input, there is only one output, something covered in chocolate. We can look at these mathematically too, but for every input, there's one output. For every x, there's one y, or we call that f of x. For every independent variable that goes into the function machine, I get a dependent variable back out. For every domain that I put in, I get a corresponding range back out. So range depends on domain, dependent depends on independent, y depends on x, output depends on input. So that is how I taught the first 11 years. And then this summer, I took my husband and I took our kids to Nashville. And the day our flight left, we went to this cool museum. It's geared towards kids. It's like a science museum. So there's all sorts of interactive displays. And there was one really cool one. It took up like one whole wing of this museum, and it was all on the human body. So there were like a little exhibit of fake teeth, and it showed, you know, like the canines and the incisors, and the kids moved a lever, and it had like a dodgeball inside, and it showed how the teeth move up and down. And then, you know, you'd walk a little further, and it had the plaque, and it told you about how your esophagus squeezes the food down into your stomach, and how in your mouth your enzymes start to digest your food. Then there was this big thing they spun around, and it showed like things bombarding each other, and it was supposed to represent what happens in your stomach with the acid in your stomach churning and breaking your food into smaller pieces, right? Okay, well, when you kept going down this exhibit, then it began to tell you, like at the very end, there was a little platform. It was like 3 steps high. So like on step 1 was a little plaque on the wall, and it explained that when your body is done with all the other stuff, you've just learned how your body absorbs nutrients and your cells carry them to parts of your body that need them, and how your blood is cleaned, right? Well, then this says that everything your body uses, whatever you put in, you have to get rid of the things it doesn't use. Or when it's cleaned the cells and it's got all the waste byproducts, those have to leave your body, okay? So on plaque 1, it explained that there are types of outputs. Okay? And this is geared to kids, right? So it explained on the second plaque then about how your outputs get, and I'm not kidding, I don't make this up, right? Their color and what chemicals make up your byproducts. Okay, and then you got to the top of the slide, and it told you a little bit more. And when the kids went down the slide, at the end of the slide, as they came out, it went because the slide was supposed to be your colon. It's like this whole exhibit ended with a slide ride, and then I thought, a great example of input and output. Whatever you put in your body must come out. So every input has an output. And if you don't believe me, babysit. Okay, somebody who's in diapers, and I dare you the whole time you're babysitting to feed them nothing but spinach, baby food spinach, and then just wait, and you will see that there is a very clear correlation between input and output. Okay? Okay? If you've ever gotten sick and you've thrown up and then you've recognized your food in, you know, you've gone, oh, I really did eat that. It doesn't taste the same coming back up. Input, output. So your body has an input, your function has an input, your function has an output. Algebraically, we begin to call this f of x, and we might give him a function like x plus 6. That means x is input, so every input I add 6. That's my whole goal. My function will have a rule. That's what happens to every input. So I take every input and I add 6. So if I input a 2, what do I get out? An 8. If I put in a 0, what do I get out? 6. So those are just inputs, outputs, domain, range, independent, dependent, all that good jazz. What we're going to do today is we're going to evaluate those from a graph. So from a graph, you're going to tell me independent, dependent, domain, range. And from a graph, you're going to evaluate a function, and then we're going to evaluate them algebraically. Questions so far? All right, so if I tell you something is a function, that means each x has one and only one y variable associated. Each x has one and only one y value. Or each part of the domain has only one element in the range it's paired with. Our vertical line test will determine whether something is a function if a line passes through 2 points at one time. Oops, I thought that was my highlighter again. Let's go back. If a line passes through 2 points at once, 2 or more points at once, it is not a function. Now, in your little boxes underneath your desk, you have 2 highlighters. You might want to grab those 2 highlighters. They might help you identify domain and range. For a reason, one of those colors is going to be your domain color, and one is going to be your range color. And if you stay consistent, this will kind of help you. So I'm going to make yellow for me my domain color, and I'm going to make purple my range color. So every time I'm dealing with domain, I'm going to use my yellow highlighter. That's also my x's, my inputs, or my independent variables. Every time I talk about range or y or dependent, I'm going to use my purple highlighter. So this is an example of discrete data. None of those points are connected. I couldn't even connect them if I wanted to because I have no idea how they're related to each other. So if I want to know the domain and the range, I'm just asking you to list the appropriate x and y values. So the domain are all the x values. Typically, we put those in our pretty little brackets. And our range are our y values. So an easy way to look at this is I'm going to take my domain highlighter, and I'm going to go highlight all the domain values, which are just my x's. Literally, I'm only concerned with where the graph is touching the x-axis. So at -4, at -3, this is an x of 0, 1, and 3. So -4, -3, 0, 1, and 3 are my domain values. I can do the same thing with my range highlighter. So I'm going to take my range highlighter, and I'm going to highlight all my range values. Range, 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 range. So that would be 0, 1, 2, 3, -2. If I have discrete points, that's probably the easiest domain and range to list. Whether they're in points, on a table, in a mapping, or on a graph, all I have to do is list the x's, all I have to do is list the y's. Things get a little bit more complicated when I have parts of the graph connected to one another, because I'm not listing individual points anymore. Now I'm listing every single x, and so I have to give an interval. So I have to say all the x's between 3 and 5, or between 8 and 10, or between whatever they are. So I've given you a couple of graphical examples of that. Our next one is a piecewise function. This is what we're going to talk about next class. So this is a graph made up of 3 pieces. So I've got this function right here. We're going to put a little arrow on it. We're going to say that it continues forever in these 2 directions, just for fun. Now, he is a function, meaning he passes the vertical line test. If I drop a vertical line anywhere on this graph, I can kind of show you that. If I take a vertical line and I move it anywhere along the graph, oop, no, I'm with the vertical line, I am only touching one point on the graph at a time. This open circle is a hole in the graph. So there is actually no point on the graph here at -1, 2. I can get infinitely close to that point. That's why I show the open circle, but it's actually non-existent on my graph. So here, I cross the graph at only 1 point, 1 point, 1 point, 1 point. Here I potentially could run into trouble. However, this open circle is not really a point on my graph. So I'm still only going to touch at 1 point. So this is a function. So those open circles represent holes in my graph. They don't really exist, but everything infinitely close to that point exists. So I still graph the hole for that reason. Now, domain are my x values. So we can also think of that as the width of my graph. So this is how wide my graph is from left to right. So if you take your domain highlighter, we can figure out what our lowest x value is. Now, oh, my graph moved. Hold on. There we go. If we take our domain highlighter, we can figure out our lowest x value. But what do these arrows tell me? So if my graph keeps going in this direction, my x's keep doing what? Smaller, right? They keep getting more and more negative, so smaller and smaller and smaller. So my lowest x value might be what? -infinity. So my domain, my x values would go from -infinity. And then I'm going to go look at the other half of the graph and see what's happening over here. So from -infinity, something happens here at x equals -1. Do I actually equal -1? But I get infinitely close, right? And my graph stops there for a minute. So my domain goes from -infinity up to -1, but it doesn't include it, so I put it in parentheses. And then my graph jumps. And so I have another part of my graph that starts with an x value over here of 1. And then over here at 3, something wacky is going on. And then my arrow keeps telling me my graph goes all the way up to what? Infinity. So if I jump, my next part of my graph is this closed circle. It starts here at x equals 1. So 1 is part of the graph. I put it in a square bracket because there's a closed circle there. Now, I don't have an x of 3 on this graph, but I do have an x of 3 on that graph. So there's no break in the graph. The graph keeps going. I have all the x's on here because my graph is continuous. There's a break here, but it's filled in right here. And my graph keeps going all the way up to infinity. So for a domain where I have a piecewise graph or breaks in the graph, I list the domain of each little section. But here, I don't have to stop because the graph keeps going. So my domain is any x between -infinity and -1 and any x that's 1 to infinity. So we could also say like x could be less than -1. We say or union x is greater than or equal to 1. So we could write these separately, or if we write them all together, union 1 to infinity, then we're really fancy. So we are close to the end of the first 9 weeks. The second 9 weeks, you're responsible for writing these in your set notation, in your interval notation, telling me from this x to that x. Somebody asked yesterday or Friday, is it okay if we wrote infinity 1, if we switch this bottom one? And the answer is no. You're writing it from smallest to greatest. So you're telling me x is any number that's greater than -infinity but less than -1. If you flip that, it isn't possible to be greater than -1 but less than -infinity. So you go from lowest to smallest. Now, range, if domain is the width of my graph, range is the height of my graph. It tells me how low and how high, the floor and the ceiling. So if I take my range highlighter, I'm looking for the lowest y value anywhere on my graph. But what does this arrow tell me? It goes on forever. It never stops. So my lowest y value is what? -infinity. So I'm looking for anything weird. Ooh, right here, I have a y value of 2 that doesn't really exist right here. But if I look across my graph, I fill it in at these 2 points. So that's actually not a break in my graph. Okay? So I have a problem with -2 with 2 right here, but I fill it in on the other parts of my graph. So we're still good. What is the highest y value anywhere on this graph? So these are all continuous. There's no break in the graph until I get up to 6. So that is the highest y value. So my range would go from -infinity up to -6. Does it +6. Does it actually touch 6? No, the open circle just gets infinitely close, so that's in parentheses. Also known as y is less than 6. Because it's a +6. And I accidentally wrote negative and I had to change it. And I didn't want to erase. Questions? Huh? So domain, we look at x values. So we go from the left part of the graph, but this arrow tells me my graph keeps going. So the left part of my graph would be -infinity. I stopped right here at -1 because my graph broke. And then I jumped to the next part of my graph starting at 1 and going all the way up to infinity. So even though they're the width of the graph, we've got to figure out where they cross the x-axis. So we're looking for fences. So the next one on your notes is a beautiful sine function. It's a periodic function, meaning it keeps following this pattern forever and ever. It's cyclic. It never stops. You'll graph this next year in pre-cal, and then you'll transform it. You'll move him right and left and up and down and stretch and compress him horizontally and stretch and compress him vertically and reflect it over the x-axis and take him and reflect him over the y-axis as well. So he's pretty cool. And you'll graph sine, cosine, secant, cosecant, tangent, and cotangent. Like that. All right. So the sine function, if he keeps going forever in the left direction, if this guy keeps going, what is his lowest x value going to be? -infinity, right? I mean, he's never going to stop. There is no fence in the left direction for x. He keeps going. And what about in the right direction, the positive direction for x? He keeps going, right? He's never going to stop. This graph never ends, so that's infinity. So the radio waves, if you're in a car and you're not listening to satellite radio, you're picking up radio waves. AM is amplitude modulated, and that changes the amplitude of the wave. And if it's FM, it stands for frequency modulated, and that changes the frequency of a wave. So if you're listening to like 97.3 in your car, it's an FM station, that's the frequency with which the waves are being sent out from the towers, from the radio station, and that's your car is tuned to pick up just that frequency of wave. They're all sine waves that radio stations use to broadcast their signal. Which is why, like if you're listening in Boerne, you can listen to 100.7, which is an Austin country station, in parts of Boerne. And then other parts it goes out. Satellite radios work a little bit differently because they're not radio waves. All right, and then the range of the function is the lowest to the highest. Now this guy has a finite range, so I'm going to look for my lowest y value and my highest y value. What is the lowest y value, the floor of this function? -1, and what's the ceiling? 1. So the range is just the height. So the range goes from a low or a floor of -1 to a ceiling of 1, and it touches both of those. So I include them in brackets. This is like saying y is less than or equal to 1 and greater than or equal to -1 at the same time. Does he pass the vertical line test? Yes, so he is a function, which is why I put him in little function notation right here when I wrote him. F of x just means y. It means the output when x is the input. So this literally means we say him f of x. That's how we pronounce that. It is not f times x. And this means the output or the y value when x is the input. So when this is the input, this just means I'm finding my y value. All right, one of the other functions we'll talk about this year is a rational function. So it will look like this, one of our parent functions. And I'll give you the equation. I think I did on your paper already. This is y equals 1 over x. And I know that I can never divide by what? 0. So in this problem, x cannot be what? So if you look, my graph gets really close here, and it gets really close down here, but it never touches or crosses the x-axis or the y-axis. Because everywhere along this y-axis, what is x? 0. And so this is said to have an asymptote, an imaginary line running through it. It's kind of like an electric fence. Okay, or one of those, like if you've ever seen a dog that has an electric collar on it, it knows where the boundary is. If you're out for a walk and a dog is stopping at one place and barking at you and it won't take a step further, it's because it has a collar on, right? It knows it's going to get zapped if it crosses that little path there. That's what this is. This is our electric fence. We will not cross or touch the y-axis. X cannot ever be 0. Now, as my x's get really close to 0, I have like 1 divided by 1, 1 divided by 2, 1 divided by 3. What's happening to my y values? So they're getting really small. So here's 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4. They're getting so small they get close to what? 0. Will they ever touch 0? I can never divide 1 by anything and get 0. So there's also an asymptote that runs along here as well. Now, if I get close to the x-axis, I'm getting 1 divided by 0.5, 1 divided by 0.05, 1 divided by 0.005, and these values are getting closer and closer and closer to infinity. So if I read this from left to right, if I'm following my graph, what's the lowest x value that this graph will have? There we go. And what's the highest x value that this graph will have? Infinity. So his domain is almost all real numbers, but what are we not allowed to have? So it's any x that's not 0, or we'd say negative infinity up to 0, but not including it, and then we jump 0 to infinity. And we do our big U for union, and then we're ready for calculus. What would the range be? Except not including? Except for 0. So the same thing for range, right? I can have negative values up to but not including 0. I can have positive values as long as we don't include 0. Is it a function? Yes, it is. It passes the vertical line test. All right, so we're going to skip ahead just a smidge. We're going to go skip 2 of these, because you know how to graph linear equations. Let's graph this guy. We're going to plot x equals y squared minus 5, which I have a square. So what do I know he is? If I have a square, what family does he belong to? The quadratic, which means it's going to look like a what when I graph it? A u somehow. But I'm used to seeing y equals x squared, and now I've got x equals y squared. So in this problem, x depends on what y is. My x is whatever my y is squared minus 5. So y is right now my independent variable. and x depends on y. Now, if I am plotting points, if I'm plotting a graph and I have no idea what it looks like, remember I pick some negatives, I pick 0, and I pick some positives. So I would select -2, -1, 0, 1, and 2. Those are my go-to points. My independent variable can be anything I want it to be. It's the one I manipulate. So I'm going to plug in a -2 for y and see what happens. So if I plug that in, x is y, which is -2 squared, minus 5. What's -2 squared? Minus 5 is -1. Please be careful when putting this in your calculator. You cannot type this in your calculator. Your calculator has been programmed to be very literal about the order of operations. So your calculator reads this problem like this. Squaring the 2, that's a 4. Multiplying it by -1, I get a -4. The only way your calculator will square a -2 is if that -2 is in parentheses. It doesn't understand that you want it to square a -2. It thinks you want it to square 2 and put a negative on the answer. If you're squaring a negative number, that number must be in parentheses in your calculator. Because can I ever square anything and get a negative? No, negative times a negative is always a positive. So I can plug in these other points. If I plug in -2 or -1 squared minus 5, that's 1 minus 5, which is -4. 0 squared is 0, minus 5 is -5. 1 squared minus 5 would be -4. 2 squared minus 5 would be -1. Now, even though I gave you the equation all flipped jabberwacky, you got to be careful here, because when I graph them, which one do I graph first? Always. When I start at the origin, which way do I go first? Right or left, so that's the x. I always go x, then y. So if I go to write these as ordered pairs, my ordered pairs are -1, -2, -4, -1, -5, 0, -4, 1, and -1, 2. So -1, -2, -4, -1, -5, 0, -4, 1, and -1, 2. And we know he's a parabola. Does he pass the vertical line test? Nope, he's going to fail it. So is he a function? Nope, not a function. But I can identify his domain and his range. So from any graph, your goal is to be able to identify domain and range. So the domain are the x values. Here's my lowest x value. What's my highest x value? What do those arrows tell me? When I have little arrows on the end of my graph. For how long? Ever, so to infinity. So my lowest x is -5, my highest x is infinity. So my domain goes from -5 to infinity. If I'm trying to find the lowest y value, that's my floor and my ceiling on my graph. But this arrow tells me my graph keeps getting lower and lower. So what's my floor? Right? It never stops. It keeps getting lower. And if this arrow here tells me my graph keeps on going, so what's my highest y value? Infinity. So my range would be from -infinity to infinity. All real numbers. There's not a number that I could get back out that isn't included. So let's look at some piecewise functions in the last 10 or so minutes. We will graph this puppy or puppies like him next time. He's a piecewise function. So he's actually made up of the pieces of other functions. So if I read them from left to right, this first piece right here is what? The line. So we know he's linear. This looks like a parabola. So he's some sort of quadratic in the middle. And then he's a line, so he's some sort of linear equation, right? Now I'll go ahead and put arrows on him. We'll say he's continuing in either direction. So if I wanted to know his domain, the arrow on the left tells me he keeps going all the way to an x of -infinity. If I read him from left to right, -infinity up to, well, I'm looking for where he stops. Ooh, Oh, I thought he stopped there, but he stops here and is filled in there. So he's still continuous all the way to infinity. There is no x value that is not included in this graph. So if I look for range values, those are my y values, my floor and my ceiling. This arrow tells me he keeps going, so what's my lowest y value? Negative infinity, and then I'm looking for y values. So all along here, the y values are included. Right here, I have a y value that's not included, but he's included over there. My highest y value anywhere on my graph is right there. So my range is anything that's less than or equal to 4. So we could write y is less than or equal to 4, or we write negative infinity up to 4. Now that's the hard part. What do you mean? Well, because I'm looking for the left values, so it keeps going that way and that way, and in the center, everything here is included. And my graph never stops, so the arrows to the left and right mean my graph keeps going. But I didn't have an arrow up to the ceiling. This is the highest point on my graph. There's no arrow that extends past that. There's an arrow that exists right here, but it isn't pointed up. So that's why my range stops here. Now the bottom part, I'm not asking you to find domain and range. I'm asking you to evaluate a function. So if this is my f function on part A, I'm asking you to find f of negative 2. F of negative 2 means find the y value, or the output, when x equals negative 2. That's literally what we're talking about here. This means, what is the y value when x is negative 2? F of x is the same as y. So what's the output when the input is negative 2? So all I have to do is read my graph. I want to know what the y value is when x is negative 2. When x is negative 2, what's the y value? 0. So f of 0, when x is 0, what's the y value? 0. F of negative 4, when x is negative 4, what's the y value? Negative 2. F of 2, when x is 2, what's the y value? Where is it filled in? 4. This is an open circle. It does not exist on my graph. F of 3 says the y value when x is 3 is 3. F of 5, the y value when x is 5 is 3. So we can read those straight off the graph. These are the same, so f of 2 equals 4 is the same as the point 2, 4. Input, output. This is the same as the point 3, 3, or the point 0, 0, or the point negative 4, negative 2. Those are all synonymous. So you're expected to be able to find the domain and range from a graph. You're expected to be able to evaluate a function from a graph. And then we're going to evaluate functions by hand. So this says, given that f of x is x cubed minus 3, find f of negative 2. So now I have my pretty little function machine. And his job as a function machine is to cube x and subtract 3. Well, x is really my what? What's another word for x? Domain, or my independent, or my input. So his whole job is to take the input, cube it, and subtract 3. So f of negative 2 means if the input was negative 2, what is f of negative 2? What is the output at x equals negative 2? What is the range for a domain of negative 2? What is the dependent value when the independent value is negative 2? What is the y when x is negative 2? So what do I replace x with? Negative 2. This is literally like a function where x is nothing but a placeholder, and I'm going to replace it with whatever my input or my x is. So the easiest way to do these is to write a skeleton equation. So f of something is that something cubed minus 3. F of x is x cubed minus 3. F of the input is the input cubed minus 3. Now what am I going to put in there for the input? Negative 2. F of negative 2 is the biggest misconception. This is just a name. This is another name for y. This does not mean I'm trying to take f and multiply it by negative 2. I don't do anything to the left. I don't get it alone. I'm not solving it. The left is simply a name. So my algebra is that I take negative 2 and cube it. So negative 2 times negative 2 times negative 2. So this is negative 8 minus 3 is negative 11. So f of negative 2 is negative 11. So this is the point, negative 2, comma, negative 11. That's all I'm asking you to do. We're not there yet. We're on the page before that still. All right, given that f of x is x cubed minus 3, find f of 3. So now what am I replacing the x with? A 3. So f of 3 means 3 cubed minus 3. What's 3 cubed? Minus 3. So this is 24. F of 3 is 24. This means I have the point 3 comma 24. Now, if I replace them with letters, I'm still doing the same math. So if I plugged in here instead of a 3, if I wanted to find f of p, this is p cubed minus 3. That's all I could do. Whatever it is, that's what I'm plugging in for the input. Now, where we're headed with this is the study of pre-cal and calculus, right? So there's a reason we do this right now. It's because we begin to explore calculus as a limit of a difference quotient. Your difference quotient is your function replaced with x plus h minus your original function divided by h. So instead of all those x's, you're replacing every x with an x plus h. So we're going to look at one of those. Here you go. Given that f of x is x squared minus 3, find f of x plus h. So in my skeleton function, what am I putting in place of x? X plus h. So whatever is here, I have to square it. I have a binomial. I cannot just distribute that square. This is x plus h times x plus h. That is x plus h squared minus 3. Huh? Well, this is x plus h squared, which means x plus h times x plus h. So this becomes x squared plus xh plus xh plus h squared minus 3. And when I combine my like terms, I get x squared plus 2xh plus h squared minus 3. And that's what I have for f of x plus h. So this is what your homework is over tonight. Next class we have a quiz in 2 classes. So your quiz in 2 classes is over 2.5 and 2.6. So it's over this, and it's over absolute value function.